recording.
Okay, hello again, people. I'm Lemos, and I'm presenting today another topic, another functional programming one that is not as hard as the previous one. So I want to talk about dyadic decomposition, right? Which is an algorithm that I implemented in Haskell 1.5 to 2 years ago, and I think it's pretty cool to share that because usually compression-related stuff they are done in imperative languages, so I wanted to change that, and I'm going to show how I did it back in the day. So let's start. So what is the use case for dyadic decomposition in my specific case? It is to interact with something called point clouds. Point clouds are basically 3D images. You can see as basically exactly as pixels, but instead of moving in a two-dimensional space, it is moving in a three-dimensional space. So each pixel is actually a point in space. That point doesn't have a volume though. It's like an atom in the middle of the space, right? So, and another cool thing is that point clouds usually they are used for modeling the shell, like the contour of a 3D object. And there are various applications for this type of stuff, as I will show in a moment. And one particular detail that you need to remember is that point clouds are huge. They can be gigantic. We're talking about like 20 gigs of stuff. Some of the applications of point clouds can be seen in autonomous vehicles like cars that need to communicate to a server, or you have like a robot on another planet, and then it's like scanning some surfaces and it's sending it back, and it's like theoretically sending 20 gigs of information back to us. We also have modeling of just mountains and stuff like that. We also have something like cars motors, for instance, and we also have this cool GIF that is actually modeling like a building using just point clouds. So this is basically like a shell of the building. We don't have anything inside the 3D objects. It's basically like to see the exterior, right? Okay, so one problem with this that you already may have identified is that they are huge, right? And that's a problem because if you're talking about a robot or a car, the car needs to be able to identify stuff and do stuff very fast, because that can, like, an accident can happen if you take so long to identify what exactly is in front of you. So you need to compress that. You need to make it smaller to send to somewhere else in order to do some sort of processing and later send it back to the vehicle. And then we have algorithms to tackle that problem. The previous state of the art in this regard was the Octri algorithm, which is basically, the idea is basically to divide the point cloud in like 8 smaller cubes, and you do that recursively until you find the points in space that we call voxels, actually. So these 3D pixels that are in space, the name of those, the name is voxel. Voxels can contain like a range of different sources of information within them, like reflectivity, color information, aside from their position, right? But in our particular case, I'm focusing only on the bare minimum, which is the position in space. We don't care about color or how reflective it is. We don't care about that. And on 2020, Eduardo Peixoto invented a new method to compress this thing, and actually it's better than the previous Octri one. And I was fortunate enough to have some classes, some like courses with Peixoto professor. And I implemented, this talk is about his algorithm, how I implemented it in Haskell. So the main idea, which is kind of silly if you think about it, but it's like these type of things are the silly ideas that nobody had, right? Which is great. That you pick the point cloud and you divide that in like two or more portions, and then you apply what we call like a light in some of the 3 axes, like X, Y, and Z, or Z, and that will make a shadow of that point cloud. And Peixoto it explored properties that this shadow can give you to compression. And I will explain that in detail. So this is the main idea. of the dyadic decomposition. This is the visual pipeline of what it does. So you pick a point cloud, you divide that into smaller point clouds, and then you choose you pick an axis, right, to do the slicing, and you also can pick the same, or I believe you can even pick a different axis to put the shadow, to put the light on that direction and point to the point cloud. And then you're going to have what you call a silhouette. And then with that, we can explore compression properties. So I will explain now what these properties are. So this is a visual representation of the silhouettes of a particular point cloud. So the first one at the top, the root, is the parent one. It's like the beginning of, it is the shadow of the entire point cloud in one direction. So as you can see, we have blue squares and white squares. The white is representing nothing, like you don't have a shadow on that portion, and the blue is representing that you have something occupying that portion of the silhouette. And then what you do is you explore the fact that if the parent of a given tree has a 0, all the subtree will maintain that 0 throughout the entire subtree. Because if I have a point cloud that is the biggest one and that it is empty, it is showing empty the silhouette, all the other slices will also have that empty, because otherwise you would not have that voxel as an empty. So for instance, in the parent there, you can see that the top left one is empty. Okay, so you don't have to transmit that information when you're going to transmit the first left child and the right child, because both of them will be empty as well, because they are a logical OR. If you pick the two children and do an OR, a logical OR, you always get back the parent. So if the parent is 0, you don't have to care about sending the information again, and that's the gotcha. Because at this point, you can remove a bunch of data out of the pilot of the data. So, and you do that, and there's another one. So if it is 1, if you have a pixel in the silhouette in the parent that is 1, and that same pixel location is 0 on the left child, you are sure that this pixel exists on the right child. You don't have to send it this guy, because if this is 1 and this is 0, this needs to be 1, because the OR of 0 and 1 is 1. So with these two main advantages, you can like remove a crap ton of data instead of sending the entire thing. And that's the genius strategy that he developed. So again, just to recap, you pick the point cloud, you slice it. We are slicing it in half. You don't necessarily need to do that, by the way. You can slice in any other sort of proportion. And then you apply a light, and you'll get the silhouette, and then you apply the strategy that I just explained, and then you're gonna have like an incredible amount of compression in the final point cloud. But there is another detail that I want to point out. So if you pay attention, the root makes two children. These two children are parents for the next round. So you always work in triplets. There's always a relationship in the with three nodes all the time. And back in the day, when I made these, when I implemented this in Haskell with a colleague in the university, we called this strategy of having this is a tree of trees, as you can see. You have each node of the outer tree has a tree in it with 3 nodes. We call this Triforce, which we discovered later that this name was already taken, which is fine for me.
Just to make myself. Did you call it Triforce without knowing Zelda's
Without
Triforce?
knowing.
Oh man.
Without knowing.
Alright.
And then that's what we're gonna be talking about. What I will be explaining shortly, the implementation. And then 2 things. Peixoto developed this idea on MATLAB, and one of my colleagues that is currently doing masters, he developed the same idea on C++. But We are not here for that, right? We are definitely not here for that. I'm here to explain how to do the exact same thing. Like, not exactly the same thing, because I will explain at the end that the current implementations in MATLAB and C++, they have advantages aside from performance that I can touch. Can touch these observations later. So this is an example of a point cloud file, right? So I want to draw your attention to the third line where we have element vertex 12. So you can have different sort of elements. So other sort of information, let's say. But we don't care about that because we only care about the spatial location of each voxel. So you need to remember that the vertex is what we are looking for. In this particular case, we have 12 vertex, and those are the coordinates for each one of them. After the end of the header, we have the coordinates of each voxel. So let's start then. So the beginning of this process is to read this thing. And guess what? We are using parser combinators as always to do that. So this is the
stop.
This is the data types that actually I didn't do this part. You did this part. It was not me. So this is the header, and this is a PLY file, which is for some reason the extension for point cloud files. I'm not gonna go with too much detail here. Just the rough idea, just to give a taste of what you can do. It works on the repo. If you want to execute, it's gonna be it's publicly available if you want to take a look later. But this is just a rough idea. So those are the data types for it. You have a header, you have data on the PLI, and the header is composed of a format and a list of elements, I guess. And again, this is purely the same parser combinator strategy that we are already used to it. So you have the data constructor as a function that you are f-mapping using applicative, and then you have, in my opinion, very idiomatic way of reading this, that you have the preamble, and then you have the elements, and then you are searching for a string called end of the header, and you search for the end of the line. The PLI parser is a little bit more complicated because it's using a for-m, but that's basically doing a for with the function HLM, sparse header, throughout all the elements data. So that's nothing to be worried about. But again, this is just a rough idea. So parser combinators to read the file. That's the main point. We're going to be exploring the encoder. So the encoder is this function here, encode geometry. It's just 4 lines. So you're gonna pick the PLI file. You can see that in the type signature. You pick an axis that we're gonna provide, X, Y, or Z, and the PLY file. And then you're gonna apply a function called build Triforce, which is basically do the main process of the entire thing. And then later we're gonna just write to a file. That's pretty much it. Long story short. So what we need to do, we need to discover what build Triforce does in a little bit more detail. So just a thing, the filter from label at the end of the last line, that is basically filtering the elements, the vertex elements that I told you guys before. So you don't need to care about that. And then after reading that, we are actually making a point cloud with the get point cloud function, and that function is a little bit extensive, so I will not be exploring that. I want to explain the PC to Triforce function. That's pretty cool. So what do we need to understand first are the types, because as you can see, we have some custom types going on. We have the iSparse Triforce tree. Discover what the heck is that. The point cloud size is just a number. It's to know what is the size, because a point cloud is always a cube. So if you know the size of one of the axes, you know the sizes of all the other axes in the point cloud. So what is an iSparse Triforce tree? So an iSparse Triforce tree is a tree of iSparse Triforce. And we have different ways of modeling images that we decided in the implementation. We have a sparse version of an image, which is basically a set of pixels. Each pixel has a coordinate, a couple of coordinates. So as you can see there, we have a type alias for coordinates. We have a data type pixel with the X and a Y. And then the image sparse is just a set of pixels. And we also have the side of the 2D image in this case. And then we have a data type for a binary tree, which is pretty standard, right? We have the node value, that is the type A, and the left and the right, which is a recursive type, and you want to end with leaves at some point. So there's that. And then the iSparse Triforce is a binary tree of sparse images. So remember, we have a tree of trees. Each Triforce is a tree with 3 nodes, and then we're going to make a tree out of those. So the iSparse Triforce tree is another tree using iSparse Triforce. Okay, always remember that we have 3 of trees. It's one of the unique applications in which having a tree of trees makes sense. That's fine. So the function that we had on the decoder is that one at the bottom, PC Triforce. That's the one that I want to explain in detail. So we have the axis, we have the point cloud that we already got from the PLY file. And let's see what we are doing there. So we are doing, whatever we are doing, we are calling a function in the middle called Triforce tree range. So, and then we are passing that a tuple to that. That tuple, it has a 0 in the first position of the tuple, and the second is the entire size of the point of the one side of the point cloud minus 1. So why is that, right? So the first step of the algorithm is to make the entire Triforce tree, but we are going to save on each node the interval of the slice of the point cloud that we will have in the future. So the first step is to create the entire data structure out of scratch, recursively. And we want to save on each value of each node, we want to save the interval, the indexes that will say, oh, this node will have the point cloud slice starting from 32 to 64 in the y axis, for instance. So the first step is to fulfill the data structure with those ranges. So that is what the Triforce tree range function does. As you can see, it picks a range, which is just a type alias for a tuple. And then we're going to call recursively, creating the entire tree from scratch. So if you're not at the end, how are you going to identify the end? You just subtract A from B, and if it's 1, you're done. You already finished the entire range from 0 to whatever the size of the point cloud is. If you're not that, you're going to create a node. You're going to put in the value position the result of that function, range Triforce, which is 3 lines up there. And then you're just going to call Triforce tree range recursively, updating the range, right? Because you're going to like divide and conquer, and you're going to do that recursively like n times. The range Triforce function picks a range and creates this little tiny tree with 3 nodes. The node AB, the leaf A B prime, and leaf B prime plus 1. That's it. That's pretty much it. So 3 nodes that will be stored on the main tree, which is the Triforce itself. After we have the data structure, we have the tree with the ranges inside each node. Now we need to actually slice the point cloud. Now it's the point that we pick the ranges and say, okay, I know the interval of indexes that I should slice, but I need to slice it, right? So that's what the slice point cloud prime function does. It picks an axis, it picks a range, and the point cloud that we provided earlier, and we slice it. And because this is happening in an fmap, we're going to fmap this function to all the nodes, passing the same point cloud throughout the entire data structure. And after we are done slicing, we need to pick a light and point at it. So that's what the slice to silhouette does. And we need to know the axis because the shadow will change depending on each axis you choose. So this is just highlighting what I just said. We slice and then you apply the light, creating the silhouette. And because we are actually doing that on an fmap, as you can see there, Triforce, on the left of that we have the less than, dollar, greater than, that's an fmap. And you're fmapping the function f, which is the one below. Okay. So what does it mean to do a slice or to make a silhouette? That's the next step. So this is the data type for the point cloud. Again, very simple. You have a set of voxels, which is again a triplet with x, y, and z coordinates, and we also have the size here that we need later. So let's now understand what it is to pick a slice of a point cloud. When you slice a point cloud, it's almost the same as doing a slice on a cake. You have a cake, you receive a cake, and then the out is also a cake, but a smaller one. So the type signature is telling us exactly that. You have the axis, you have the range, and you're going to receive the entire cake, and the return will be a piece of it. So it's basically a filter. You pick the point cloud and you apply a filter because you can have access to the coordinates of the voxels, right? Which is what the function f is doing. It is picking the range that you provided, and it's also picking the voxel itself that you're going to use to filter it. And for each voxel, we'll do that comparison right there. That obviously that depends on the axis that you chose before, so that's why we have 3 pattern matching lines there. So if you have, for instance, the x-axis, you're gonna do the u, because voxels, they don't have x, y, and z. They have u, v, and w for some reason. I don't know why, but it is what it is. So if you chose the x-axis, you're gonna do something different than if you chose the y and z, and that's pretty much it. So it's basically a filter. To slice the cake is just a filter. And what about making a silhouette then? A silhouette is you pick an axis to choose from which point the light will be at, and you pick the point cloud, and then you're gonna have an image sparse. So an image that is actually just a set of pixels, each pixel with their own coordinate, which is basically just wrapping in the data type of the image sparse and applying an auxiliary function called slice to pixel.
I have one question. Just before you keep going on this, can you explain? I'm not sure if I got what the silhouette is. Like it was showing the like you were saying the light, right? Like that was the first slide. So it's like, can I say it's like some sort of metadata for what should be stored on the points?
Okay, so let's pick this book here.
Okay.
Do you agree this is a tridimensional book?
Yeah.
Okay. Do you agree that if I pick a light and put it here, you're gonna see a rectangle there?
Oh, I see. So it is the I get it. So it's like the shadowing of that thing,
exactly,
like in another dimension, right?
Something yeah, one of the dimensions. You have to pick one.
Mm-hmm.
So that's why you need to pass the axis all the time, because you need to decide from which you have a cube, from which of the axes the light will be at.
Mm-hmm.
And what we are making with our images being sparse or raster, that I will show later, the images are the shadow that you will make at the other side of the light.
Mm-hmm.
It's exactly as I did with the book there.
That makes sense.
And because the axis is important to understand, to put the light, with the slice to pixel L function is also picking the axis as a parameter. Mm-hmm. And depending on the axis, we need to do it changes the way that we need to transform the voxel to a pixel, right? Because a voxel is again 3-dimensional and a pixel is 2-dimensional. We need to shadow each voxel to the shadow itself. And there's a gotcha, right? Because we can have voxels that in one direction they are the same because they produce the same shadow, right? So if you have a point here and you have a point here and you put a light here,
see, yeah. Mm-hmm.
One will be on top of each other. That's why it needs to be a set.
Mm-hmm.
Because you need to exclude those duplicates.
Yeah, makes sense.
Mm-hmm. Okay. And that's why we're doing a set union there, because again, this is a set and you want to remove duplicates automatically with the set, using the set as your abstraction. If you use a list, it's going to be a lot more painful because you need to search the list to see if that already exists. So that's kind of bad. Okay, so now we know what build Triforce does. Build Triforce does, it filters from a label to get the vertex, and then transforms that data to a point cloud with the data type that I just explained. And then it calls that PC to Triforce function that I showed it before, which is actually this function right here, which is picking again. Just a reminder, it's creating the entire tree with ranges, and then it's populating that ranges with a slice and a silhouette. Like it picks the range, transforms that to a piece of cake, to a slice of point cloud, apply a light, transforms that to a silhouette. So now what we have an entire tree, each node with another tree, with 3 nodes. Remember Triforce, always remember. And each node of the Triforce has a silhouette now. That's simple. Not a lot of like ifs and elses, and well, if you know MATLAB, you know what I'm talking about. Anyway, so now the next step is to discover what this is doing. Now it's time to write that down. We already have the data structure. How can we convert that to a binary format, right? So if you ask me, what you need to do is to pick the outer tree, which has the smaller tree inside. You need to convert each Triforce to a bunch of ones and zeros. And you need to apply that mechanism that I explained earlier, that you can save data using the shadow properties between the three. The three, the parent, the left, and the right. And then after you transform each node, you fold them. You fold the entire tree in one go. Because each node has a bunch of ones and zeros, and what you want to do is to concat them together to have a single binary sequence. So it's a concat map is actually a version. It is the specific list version of a fold map. Because we are using lists to model the binary format in this case. So let's understand what right root silhouette does for now. This is the first one. We're gonna go to the other one later. Okay, so this is the main one of the main functions to the encoder. So you have a right root silhouette, which is picking an Sparse Triforce tree, which is again that gigantic data structure is a tree of trees, and you want to convert that to a binary format. Okay. So what do we need to do? Here we just want to pick this function specifically. You want to just write down the main parent, the root of all the tree. Because if you pay attention, if you go back to the Triforce, this is actually worse because I think okay without the issue. If you pay attention to the Triforce again here, every single time we don't send. We need to be careful because we are repeating nodes in the Triforce. The children of one node are the parents of the nodes below. What that means is that you never send the parent. You never encode the parent. You need to skip the parent and always do the children. Because otherwise you're going to have duplicates along the way. Because YL1 and YR1, they are appearing again later. So the only exception to that case is the first root of all. The first root of all, you need to send that. That's what the right root silhouette is doing there. Every other case...
Wait, like they appear again? Okay, that's an exception, right? Because you don't send the root from the perspective you were in, but you send the root of the children. Not the root of the children per se, but what the children have, which is the new tree.
Yes.
Okay.
Yes.
Makes sense.
Yeah. So
because they're always the root of the new thing. So
exactly.
Okay. Yeah.
You never send the parent because the parent was a children of the other the level above.
Mm-hmm.
The only exception to that case is the first root. The first root you need to send that. Because that's not not following this property that only applies for the other nodes. So that's why we have a plus plus. That's why we are concatenating two lists. Look there, right root silhouette. That's picking just the main root of all and writing it down, and we are concatenating that with another function. That's why we need to concat, because there are two separate cases. One is the exception, and the another one are the general case that you just do not encode the parent. You forget the parent. We're going to look at both of them separately, well, because they are separate at the moment. But okay, so right root silhouette. So what that starts? Let's start with the get root function. The get root function picks this entire monstrosity of trees and do get value twice. Because if you do get value, you're going to pick the first node, and this node you have another tree, I remember, and then you apply again get value. So then you pick the main root of all the other trees. To do the transformation to binary, I am using another format for an image because, like I said, we have a sparse image, which is a set of pixels, and we also have here I'm going to introduce the raster image, which is a matrix because it's so much easier to do the masking, to apply masks later. And we will have to apply masks because remember, the Triforce it is assuming that these three nodes they have a relationship in which you can exclude information because you're already sending it before. That's important. So let's see first. This is the main function that that does the job, and this is the first function that matters for us. This is sparse to raster. So it picks an image sparse, which is again a set of pixels, and transform that to an image raster, which is a matrix of the same thing basically. But instead of, because the coordinates in the matrix they are already there, you don't need to save those coordinates. We just save the information if that pixel is occupied or not, if it's empty or not, and we call that occupancy. So it's basically a fold. You fold the set and you keep reinserting. So you pick up a pixel in the set, apply that to the matrix, and you keep doing that with the normal fold. No problem with that. And then we have the transformation of the rasterized image, which is a matrix, to a binary. So we pick the matrix, we transform that to a list, and then we map a function that, oh, if you are occupied, you should be a 1. If you're not occupied, you're going to put 0. Okay? So again, this is the main father of the entire tree. So this guy, you need to send all of it. You cannot compress that guy. That guy needs to be sent entirely. And then you might say, okay, that sucks. And then I can say, yeah, that sucks, but you are sending just one 2D image of the entire point cloud. The compression benefits come now because all the other children of the entire Triforce tree, you're going to be able to compress that a bunch. So this guy, again, you literally send it all. The father of all, you send everything related to it. Okay, now it's time to know what happens if you're not an exception. What happens if you're not a father of all the tree? Then you're going to do something different. And that's where the compression is. So let's see what the Triforce to binary does. So this is the function. Right? So this function is, again, a concatenation. But we need to apply a mask now. Why do we need to apply a mask? Because we can exploit that fact that, oh, if the parent is already 0, you don't need to send that information again. The children, of course, will be 0. Because they are a logical OR of the logical OR of the children makes the parent. And the only way to the result of an OR to be 0 is if both of them are 0. So you don't need to send them. So that's what we're doing. So the first apply mask encoder on the left, it is using the parent as the mask for the left child. And then the one on the right is picking the left child as the mask for the right one. So let's see what that mask does. So if V1 is the pixel of the parent and V2 is the pixel of the one of the child. So V1, if V1 is empty, which is the first guard, not V1, right? If the parent is empty, I don't need to send anything, so it's nothing. Because if it is, I need to also to be by construction. But if my parent is 1, I may be an occupied pixel as well, so I need to send my information. And again, there is that benefit that if the parent has an occupied pixel and the child on the left doesn't, during the decoding process, you know that the right child needs to be 1, because if this is 0 and this is 1, this needs to be 1 as well, in order to the OR to be equal to the parent. So that's important to keep in mind. The encoding process and the decoding process, they explore different properties of the silhouette, which is kind of like weird, but okay. So that's what is an apply mask encoder does. It's basically picking each element of 2 image rasters. One will be considered a mask for the other. And again, for the left child, you use the parent. And for the right child, use the left child as the mask. And then that's pretty much it. And because we are using, and because this function apply mask encoder, it returns a maybe, we actually need a different conversion to binary, because now we have a matrix of maybes instead of a matrix of booleans as before. So what you're going to do, and this is where the compression comes, right? Because if you see there, we have a filter, is just. That means that we're not going to send information every time we see nothing. So every time this function here returns a nothing on that guard, we will not send that info, the binary, because you are filtering only the justs. And then we pick the just, and if you are inside the just, you have a true, you're going to transform that to a 1, and if you have a false, you're going to transform that to a 0. And that's it. That's the entire encoder. So let's recap to see, to have a little bit of a bigger picture. So pick the file, you use Sparse combinators, transform that to a point cloud. You pick the point cloud, you slice it and apply the lights to have a Triforce tree, which is a tree of trees, right? And then you use fold map to transform that to a binary, and you need to take care of the exception, which is the father of all the tree. In every other case, you don't send the parent information. And then after all of that, after all, I'm talking here for, I don't know, 30 minutes, 35 minutes, I don't know, you can say, okay, what about decoding then? And the answer for that is the decoding works. It is also in the repo, but it's a lot more complex to decode this. This is where, yes, exactly, yes. You need to pay attention to like, oh, the father, the parent of this node was 0. Okay, so I need to populate the left and the right with zeros as well. Oh, the parent came with a 1. Okay, so now I need to pay attention to the left, because if the left is 0, this is actually a 1. No, I'm not done. So I'm not going to show the decoding process because it's a lot more extensive, and it's actually not that great of a Haskell code, to be honest. But like I said, I did that 1.5 to 2 years ago, so it's not my finest work ever. But I want to borrow specifically what was said on last week, right? So I want people to understand that if you have a problem in a certain domain, which is in this case is compression, people go automatically to MATLAB. People go automatically to C++. And I don't want that to happen, because as I try to demonstrate that we have powerful tools in functional programming that can alleviate a lot of the burden of doing this by hand, because all this code I did from scratch, right? And I can't even imagine the mess that this would be in an imperative language in which you don't have this functional composition to help you. You don't have powerful functions like fold map to facilitate to make the entire binary at the end. Those things are just like you don't want to waste your time doing this type of stuff. You want to waste your time with the actual algorithm, and you want to use a tool that facilitates that you don't need to care about minor details, implementation details, and you only care about the process that you are focusing on. And then, as an invitation, as my final slide, is that people may say, okay, but you are totally ignoring the performance, right? The C++ code is being submitted to MPEG. It's going to be the state of the art, right? Because it's fast as heck, and I know. But for that, I say, okay, now I am done. Wait, you mean having multiple children instead of just 2? That's a phenomenal question. Because no, let me give you the spoiler of the answer before though. So there is in the I think that 2021 or the 2022 paper from Peixoto, there is an implementation with what he calls a single mode. A single mode, when you activate single mode on his MATLAB code, it actually converts a binary tree to an N tree. And that instead of having to slice at half each time of the tree, you will slice with the range of 1. So you have a slice of the point cloud with only 1. And you're going to do that n times. And the performance and the compression is better. The problem, the reason that I didn't implement this when I was doing it 2 years ago is because this completely breaks the Triforce abstraction. Yes. Yeah. No. It's not that I couldn't do in Haskell. I could totally do it, but I didn't want to lose the Triforce abstraction because this was so like. This was a Jew's idea, by the way. I didn't make the abstraction because when he noticed that, oh, dude, you have trees that these like the triplets they need to be connected in different, and then he said, oh, why don't you call that Triforce then? Who cares? And then I said, okay, and then we made the thing on top of that. So it is totally possible.
I made my question and I was muted. But anyway, that's it. I guess people.
Oh, you made the question on the recording.
Like I was muting myself on OBS. But anyway,
oh, okay. Okay, so but just for the archive, your question was about instead of having a binary tree to slice, you do I don't know 3 children 4 whatever, right?
Mm-hmm.
And the answer is that it is what it is done. This is the best to have the best compression ratio. You actually do single mode.
That's the other question. Do you have benchmarks on this?
Yes, I do have benchmarks on this. It's not. The benchmarks are not in the presentation, but I do have the data in another file that
do you have an idea? Like something like this, like for I don't know 20 gig. I don't know how much you tested or something like this.
Okay, so I will show you. I will open another browser here. I already stopped sharing my screen, right?
No, you're still sharing it.
So stop stream. Okay, so I will open the original presentation that this was made, and there we have the data. I didn't put the data here because my focus was on explaining how we model it in a functional programming manner. It is pretty impressive, by the way. Oh, and by the way, the guy that participated in the first state of the art using the Octri algorithm instead of dyadic decomposition, I also had classes with that guy. And I'm pretty impressed he got debunked though, because that guy is a monster. Okay. So.
You're still
okay, so on a point cloud, no, I'm not sharing. I'm just gonna say it out loud. Here. So on a point cloud of 2 of the power of 32, that's the size of the point cloud. That like one axis is the size of 2 to the power of 32.
Okay.
Like again, 20 gigs is gigantic. Mm-hmm. We got 105 bits per voxel. So for each voxel in the point cloud, we wasted 105 bits in the final file. So low is better. The lower the better. Mm-hmm. And using dyadic, we went from 105 to 48.
Okay, that's a good benchmark. I mean, I would have to know other algorithms, right, to compare. But you said this Octri was the best one.
Yeah, the Octri was the best one before.
That's a huge difference. That's a very huge difference.
No, wait. This is not a comparison between the Octri and the dyadic decomposition. This is between picking the original point cloud with no compression.
Oh, I see. Okay. Mm-hmm.
Yeah, it is not that huge. It's not this amount of huge the difference of Octri and dyadic. Okay. There's a reason the Octri was the king before. Mm-hmm. The original point cloud has 105 bits per voxel, and after applying dyadic, we got 48. But there is another piece of data here. In our implementation, which I'm assuming is the like naive dyadic decomposition, because I think Peixoto provided more more like more alternatives to compress even more and more and more. And looking at the neighbors, for instance, applying some sort of image compression that we used to JPEG and stuff. Probably his results are better because we noticed that as the point cloud grows, the compression got worse. At the point that at some point it got even bigger than the original one.
Yeah, that's I found it strange because the case for JPEG, I think if you try to compress, depending on the algorithm, the size of the image actually increases. So it's
yeah, we got that with 2 at the power of 128 of the size of the point cloud. That phenomenal result that I showed you, it was with the 2 at the power of 32. So it's not that like it is pretty huge for our standards, but for point cloud standards, that's not that gigantic. So yeah. So yeah.
Okay.
So these are the benchmarks that we did back in the day.
So okay, you published the papers. By the way, let's add on the papers links on the references on the video. But that's it, just so people can see. Because you mentioned the authors, but I think like it's harder to find that way.
Yeah, I think there are 3 papers. There one the 2021 with only Peixoto. There's there is one in 2021. No, the first one was the one that I showed, 2020. Then there's a 2021 one. I think that this was with Edu, and the 2022 is also with Edu. And then, well, they are adding extra. For instance, Peixoto explored the idea of doing the normal dyadic decomposition, and then at some point in the middle of the slicing, activates the single mode. So no more binary division. Just go straight up to one size slices. So, and then there's also the question, can you infer which axis provides you the best compression? So those type of questions he already explored, of course.
You know what I think is cool about this algorithm? Like, if you look at compression, from what I remember, okay, I don't know that much, but from what I remember, they are not that easy to make it parallel. You know, like distributed or just like concurrent. And this one seems to be very easy, right? Because you're just like you only have it's literally a map, like a segregate, right? And then you reduce in the end. So it's like it's very well separated. It's very decoupled, I would say.
Exactly. The only common thing between the threads would be the initial point cloud. Everybody else would be doing their own thing.
Almost looks like no, I don't think you know the pi calculation, like Monte Carlo algorithm.
Yeah,
they're like central, right? So you have a central unit, and then you split into different nodes, but they all communicate with this dude. So I think it would be something like this, like.
No, but there isn't any communication.
No, you need to on the reduce. I mean, like you.
Oh, on the reduce, yes.
Yeah. So.
But yeah, so and the fact that he's already exploring the same technique of trying to not send a voxel based on the neighbors, that is like video strategy compression. Because you in video compression, for those that don't know, you actually use the previous frame to not have to send extra data, right? This is like temporal compression, but there is also physical compression, in which in the frame itself you pick a pixel and look at the surroundings, and that's like, man, if he's already doing stuff like that, like there's no chance. Like it is already high level stuff. If I'm not mistaken, he's competing with the Spanish people or something like that, because they copied his idea and did it and made some modifications and stuff. But don't quote me on that. I don't know the details about it. Just know that some other people that speak Spanish, they are trying to win the fight, to win the MPEG.
De hermanos. Anyway, so can we stop recording?
So Nathan, do you have any comments or questions? Just before we finish here?
Back.
No, he is back.
There's a message.
No, he's typing.
Oh man, our Lisp stuff is showing here.
Yes. Especially the part that I saw before. I don't remember which part I showed you before, but anyway. Okay, now you can finish the recording now.
Okay,